we looked at, well, we kind of slowly introduced ourselves to the definition of a Fourier series. And we looked at one example of one just to illustrate it, which was the square wave function, or the more or less the Heaviside step function kind of over the interval minus pi to pi. We looked at its Fourier series. Okay. So if you weren't here at this lecture, you can see the recording of it online in the usual place, and also there's a little bit of a interactive demo, a Sage cell showing the Fourier series for the square wave function, and the way that as you add more and more terms to it, you get a better and better approximation of the objective function. So this was the setting. This kind of thing in equation 3.1 here, this is a Fourier series for a function f. It's a way of representing f as an infinite linear combination of basis functions. And the basis functions are the constant function, so you've got some kind of constant out here in front, and then all these cosine functions, cosine nx, for each positive integer value of n equals 1, 2, 3, and so on, and all the sine functions, sine of nx, okay? And just like Taylor series, you know, the exact equality holds for the potentially infinite series. If you take any finite initial part of it, you take any partial sum on the cosines and partial sum on the sines, you get an approximation to the objective function f. And as you add in more and more terms, this approximation gets better and better. Now last week we also described this in very linear algebra language. We said that we had a space of functions, f satisfying certain conditions. That was a vector space. And the basis functions, the constant one, the constant function of value 1, all the cosines and all the sines, this was an infinite basis for this vector space. And so this expression here in 3.1, you think about it in kind of linear algebra terms. You have an element in the vector space, this function f, expressed as a linear combination of the basis functions. Okay. So keeping on that theme, so this set f here at the bottom of the page 59, this is the set of basis functions. And if we have a set of basis functions, well, we need an inner product to go along with that. So the inner product will allow us to extract the formulae for the coefficients that appear in the linear combination from taking inner products of the vector with the various basis functions. So what we're going to look at first today is these examples 3.1 and 3.2. And what these are doing in examples 3.1 and 3.2, they're proving various parts of the key results that this set of functions here, this set of basis functions, is an orthogonal family with respect to that inner product. So to say it's an orthogonal family means that if we take any two different functions from this set and take their inner product is going to be 0. Okay? So just like when you have the normal dot product of geometric Euclidean 2D or 3D vectors, when you take their dot product, if the dot product comes out as 0, that has the geometric interpretation that the two vectors are at right angles to one another. Well, the same language is used here. We've got two of these basis functions. If their inner product with each other is equal to 0, we say that they're orthogonal. Okay? This is an important property that we need to set up the theory of the Fourier series. So example 3.1 and 3.2 prove various parts of that orthogonality result. So we'll have a work through those examples together now. Okay? On the visualizer. So this is going to be example 3.1. So let's have a look at it and see what it says. I think this is proving. So if we take a cosine and a sine function to show that they're orthogonal with respect to the inner product. Okay? So the inner product, this is defined as, well, if you take the inner product of a phi and a psi, two functions, this is defined as integrating the product of these two functions over the interval minus pi to pi. Okay, this is the definition of the inner product. You can see it at the top of page 60. It's very much, it's the standard inner product to have on a vector space of functions defined over a certain interval. And it's very much the continuous analog of the more familiar vector dot product that you're used to seeing in dimensions 2 and 3 for Euclidean vectors. The dot product of two geometric vectors is the sum of the products of their corresponding coefficients. Okay? Well, that's exactly what's going on here in the continuous sense. We're taking the product of values of the two functions correspond at the same argument, x, and we're summing up, or in the continuous sense, we're integrating all these products up across the whole interval of interest from minus pi to pi. Okay. So proving that the cosine function and the sine function are orthogonal, that means we want to show that they have an inner product of 0. Okay. So if phi of x is this function cosine m of x, and so that's phi of x, and psi of x is one of the sine functions, nx. So n and m are both two integers greater than or equal to 1. We will show here that the dot product of this phi and psi is 0. Okay. So that means that we say the two functions are orthogonal. Okay, well, it's just an exercise in evaluating the inner product. So, we just apply the formula. So this is by definition of the dot product. This is what it is. We integrate the product of the two functions. So we just put in the definition of the two functions. So we're integrating cosine mx times sine nx dx. We're integrating this product across the range minus pi to pi. Now this is a product of a cosine function with a sine function. So there's a nice trigonometric formula to turn that product. In general, integrating products of functions can be a bit tricky. You might need integration by parts. But the simplest way to kind of find this is to use the trigonometric formula that takes a product of a cosine with a sine and gives you a linear combination of two sines. Okay. So we'll use the formula. We'll use the formula that cosine A times sine of B is in fact a half of the sum of the sine of the sum and the sine of the difference. Okay, so it's a standard formula from trigonometry that we can use. And that will turn our product of cosine and sine here into just a sum of two sines, which we'll be able to integrate using just the standard formula for integrating a sine function. So we're going to have a factor of a half out here, integrating from minus pi to pi.
Is the second sign meant to be a constant?
The sign here?
Yeah.
No, I believe it's a sign.
I mean, sorry, the first one. Because the visual.
I'm not following that formula.
No. Which one was it?
Well, I did.
Well, I thought you had to do that because it starts with that anyway, doesn't it? You know, cos and sine.
No, you're looking at the wrong thing. No, we're evaluating that inner product.
Oh, sorry.
Yeah. Okay. So we'll have here the sine. Now, so a plus b, so we've got to add these together. So you've got m plus n of x, and then you've got sine, and then you're subtracting, it was b minus a, so this is going to be n minus m of x dx. Now this kind of splits into two cases. You have to treat this maybe in two different ways, because if n is equal to m, then this coefficient here is going to be 0, sine of 0 times x. So that will always be sine of 0, so we'll always have a 0 there. Whereas if n is not different from m, we'll have a non-zero multiple of x, so you will genuinely have a sine function. So there's just two kind of cases. So assume for the moment that n and m are different. We'll come back and look again and settle the case of where n and m are actually the same. Well, if they're different, then we can just go ahead and integrate this using the rule for integrating sine functions. And so this is minus the cosine of m plus n times x, and we need to divide by m plus n. And it's also minus the cosine of n minus m times x, and we divide by n minus m also. And this gets evaluated at minus pi and pi. Okay, maybe this is complicated to work out, but hang on a minute. When you evaluate this at pi and minus pi, you're just looking at cosine of n plus n times pi. Well, m and n are two integers. So you're looking at cosine of an integer multiple of pi. Well, that's going to be either plus 1 or minus 1, depending on whether the sum here, m plus n, is odd or even. And similarly,
So I don't understand what you meant by what you just.
so we have to substitute pi in for x. So when you put pi in for x here,
But how will that change the even?
well, because you're looking at cosine of an integer multiple of pi. So think about it. You think back to the unit circle in the complex plane. An integer multiple of pi is either this point in the unit circle or this point.
Sure.
So the cosine value, which remember is the x coordinate at this point, is either going to be plus 1 or minus 1.
Sure.
And that will just depend on whether the sum m plus n happens to be an even number, in which case the angle will bring you around to here, or if n plus m is an odd number.
Yeah, how do I thought they're both odd. 1 or minus 1, isn't it?
Well, I don't know which one. I don't. All I know is that they're two integers greater than 1.
Okay.
One of them could be odd, the other one even. They could be both odd. They could be both even.
How do that alter the circle? How does it alter?
Well, it's because it's to do with the total angle. You're looking at an integer multiple of pi.
Oh yeah.
Yeah. So you either, when you go around an angle which is an integer multiple of pi, you either end up at this point here on the unit circle or at this point.
Okay.
So that's why the cosine value is just going to be plus or minus 1. Okay, but even more than that, in fact, I don't think it really boils down to that here actually. So cosine of integer times pi is either plus or minus 1. But more importantly, we don't even need to get down to it on that level because they're just cosine functions. So when we equal to cosine of plus x. changing the sign of the argument to cosine doesn't change the value. So actually, sorry, that's more the relevant observation. So when you evaluate this first fraction at pi and evaluate it at minus pi, you're going to get exactly the same value, which you're then going to subtract. You subtract the evaluation of the upper limit from the evaluation of the lower limit. And similarly with this function here, because this is just a cosine of x. So when it gets evaluated at pi, it has a certain value, plus or minus 1. But when you evaluate it at minus pi, it'll have the same value, plus or minus 1. But they just get subtracted, because you're doing this evaluation at the end of an integral. So this is just equal to 0, as required. Okay. Now that was in the special. Is that okay for everybody? So actually, sorry, I mean, it's an interesting observation to say that cosine of an integer multiple of pi, that's either plus or minus 1. That should always be in our minds. But actually, we don't need to make use of that fact in particular. We're just using this other fact about cosine, that it agrees on positive and negative arguments of the same absolute value. So when you do the evaluation at the end of the integral, you just get 0. And now that was in the special case where n was not equal to m. So we should just deal with that case. If n is equal to n, so let me come back to this expression here, but we have to think that n is equal to m. Well, then this is going to be sine of 0 times x, which is just 0. So then the inner product is just going to be half the integral from minus pi to pi, sine of m plus n times x plus 0 dx. Plus 0, because this sign up here is now sine of 0 times x, so it's just 0. 0 there. And then this will equal to 1/2 of minus cosine m plus n x over m plus n, evaluated at pi and minus pi, which will equal to 0 as before. For the same reasons, sorry, I'm going awful small there. For the same reasons, because cosine is this function which takes the same value on positive and negative arguments of the same absolute value. Okay. So that shows, that's part of the whole result, that all these basis functions form an orthogonal family with respect to the inner product. Okay. The other parts of the other cases of orthogonality are in the exercises. There are other kind of exercises with integration to do. So i.e., if you take the inner product of the constant function 1 with any cosine function, you always get 0. You take the inner product of 1 with any of the sine functions, you always get 0. There's lots of different cases. You take the inner product of any sine nx with a sine one family of pairs where you take one of the sine functions and one of the cosine functions. Okay? But every other type of pairing, they're always orthogonal as well. Okay? I think Yeah.
What's the general definition of orthogonal, please?
The general definition of orthogonality is a pair of objects in a vector space being orthogonal with respect to a certain inner product. And it means that the inner product evaluated at that pair is 0. That's the general.
Right, okay.
And when you think in terms of the dot product of geometric vectors, either 2-dimensional or 3-dimensional, then that exactly is orthogonal. That's exactly the geometric notion of being perpendicular. Okay? So that kind of geometric idea generalizes to general vector spaces, and it becomes this concept of orthogonality with respect to a certain inner product. Okay? So you can have the same, as you're seeing with Stephen, you can have a vector space, but many different inner products defined out. Okay, the next example, example 3.2, we'll look at. So this looks at what happens when, okay, so if we accept that the inner product is orthogonal, or that this set of basis functions are orthogonal with respect to the inner product, what happens when you take the inner product of a function with itself? What kind of values come up here? So if we let phi of x equal psi of x equal, so let's take one of the sine functions. What's the inner product of phi with phi? So really we're just, probably didn't need to mention psi and phi here, but what happens when you take the inner product of one of the sine functions with itself? Okay, well by definition, this is the integral from minus pi to pi of the product of the two functions. Well, it's the same function multiplied by itself, so we're looking at sine squared. So we're integrating sine squared over the interval minus pi to pi. And again, another trigonometric formula will come to our aid here. This time we'll use the formula that says sine squared of a, it's one of these double angle formulae, is a half of 1 minus the cosine of 2 times a. Okay. So sine squared of a looks kind of awkward to integrate. The square of a function, its products, again, you'd have to use some kind of chain rule or integration by parts or something. Whereas if we can replace it just by, okay, a constant and a cosine function, then we could just use the standard integral of the cosine function. Okay. So applying that here, this will, we again get a factor of a half. And now we're integrating 1 minus the cosine of 2nx dx. Okay, that integral now looks very standard. So it's a half. Integral of 1 is x. Integrating cosine, that integrates to sine. So we've got sine of 2nx. But we need to divide by 2n as well. And we're integrating over the interval minus pi to pi. So we've got to evaluate that there. So how does this evaluate? Well, we need to substitute pi in for x and minus pi in for x and subtract them. Yeah, that's okay. That will just give us 2 pi. Then you need to substitute x equals pi and x equals minus pi into this expression here, sine of 2nx. But there, you'll just be evaluating sine at some integer multiple of pi, an integer multiple of 2 pi. N is some unknown integer, positive integer, so we'll be evaluating sine of n times 2 pi. Well, what kind of value is sine of n times 2 pi at? Very nice, simple value. 0. Sine of 2 pi is 0, sine of 4 pi, sine of 6 pi, sine of minus 2 pi is 0. Okay? Always we have sine of any integer multiple of pi is equal to 0. So this will just become a half of pi minus pi, so that's just the evaluation happening at x. Plus well, I'll just put that 0 there to indicate since sine of any integer multiple of 2 pi is always equal to 0. So it's a half of pi minus pi, so it's just pi. Half of 2 pi. That's a nice value to pop out from the inner product of one of the sine functions with itself. So you can also show, in a similar way, that if you take the inner product of any of the cosine functions with itself, you also get pi. You also get pi out as well. And if you take, the only other remaining case is the inner product of the constant function 1 with itself. Well, that's just the integral from minus pi to pi dx, which is just 2 pi. So this 2 which comes in from the inner product of the constant function 1 with itself, that kind of explains the presence of this kind of factor of a half in front of the a0 here. I mean, you could have, this whole thing, half a0 at the front of the Fourier series, that's just the constant term in the Fourier series. We could have chosen to just write that as a0, but we choose to rescale it as a half of some parameter a0, and kind of the origins of that is the fact that this factor of 2 is coming up there in the inner product of the function of itself. So those examples have introduced us to the fact that the family of basis functions is orthogonal with respect to the inner product. And we also see the values that come out when you take the inner product of one of these functions with itself. Okay. So now we'll look at the formulae for the Fourier coefficients. Okay. So when you look at the notes there, in section 3.2, so now we're thinking about how do we actually go about finding one of these Fourier series. So if somebody hands you a function, we want to find its Fourier series. So what that means is finding the values of these coefficients, finding the a0, all the an's and all the bn's, finding their values, and then you know the kind of components of the original function f, the components for its linear combination as an infinite linear combination of cosines and sines. Okay. Its Fourier series. And the formulae are given here. Now they're given here in their integral form, so they're all expressed as 1 over pi times a certain integral. When you look at these integrals, they're integrals of, okay, well the a0 is just integrating the function f of x, but the other an's are integrating f of x times cosine n of x, and the bn's are integrating f of x times sine n of x. So these are really inner products of the function f with one of the basis functions, either the constant function 1 multiplied by f here, or the cosine function multiplied by f, or the sine function multiplied by f. What these formula are inner product formulas. Okay. So if we look here at section 3.2, these formulae can be expressed as inner products. So the coefficient A0, you can write that as, so this is another form of that integral formula, but just using the inner product to represent the integral. Because that's how the inner product is defined. It's defined as the integral from minus pi to pi of the product of these two functions. And similarly, the other ANs are 1 over pi times the inner product of cosine nx with f. You could write it the f first and the cosine afterwards, remember, because inner products are symmetric, of course. So that's applies for any n greater than or equal to 1, and the bn is 1 over pi times the inner product of the sine function with f. You should probably write f of x there since I'm writing x there. F of x. And this kind of gives a clue to how we're going to. Now, this isn't quite a proof of these Fourier series formula, but it is at least some motivation for them. So if you look at example 3.3 here, so I won't call this a proof of the Fourier series, but it's motivation or some justification for these formulae for the Fourier series coefficients. So what does example 3.3 say? It says, okay, let m be an integer greater than 1. So we're going to use the existence of the Fourier series to find an expression for the inner product of f with sine of mx and show how this produces the above formula for determining the Fourier coefficient Bn. So if we assume that the Fourier series exists, so assume that a Fourier series for a function f exists, and it exists like this. So we have f of x is a half of some a0 plus this linear combination of all these cosine functions and this linear combination of all these sine functions. Can we assume that this kind of expression for the function f exists? Then, well, our aim here will be to find out what one of the b coefficients is. Okay. What we do is we take the inner product. We take the inner product of both sides with the function, with one of these sine functions, sine of mx. Okay, this is what the is what we're aiming for here. Now n is the index, which is running over all the integer values 1 up to infinity. But here I'm talking about one particular one of those. So I'm using the letter m just to distinguish it from n. So what we have here is, so we'll take the inner product of the left-hand side with sine of mx, and we'll equate that with the inner product of the right-hand side with sine of mx. I won't write it, so I'll just write it like this. Depending how you put it down on your page, you'll probably be able to do something like this. So we take this whole expression here, and this all goes in the first position. Okay, won't bother rewriting it all that again. So you have to imagine here, see f is equal to this, since it's Fourier series. So we take the inner product of f with the sine function, sine of mx, so we just stick the whole Fourier series into that first position there in the inner product. Very clear on this? So I have this whole, I mean, I could have written it out, I just have to have these angle brackets really far apart, fit in this whole expression here in the first position. Now what we're going to do, and it's skirting over some technicalities, but you're familiar with your work with Stephen that an important property, one of the important defining properties of inner products is that they are linear in both of the variables, both of the positions, in the first argument and the second argument. So if we're putting in a big linear combination of stuff into this first argument, I'm going to allow myself to expand it out and say this single inner product is going to be the linear combination of all the individual inner products. Now there's some technicalities to deal with here because I'm using linearity over an infinite sum as opposed to over a finite sum. Finite sum doesn't present any problem. That follows from just the basic form of linearity property for a sum of two objects. That can be extended by induction, if you like, out to any finite number of objects. When you've got infinite sums, you have to be a little bit careful. There's issues of convergence to deal with, and so on. But I'm just going to, for these purposes here, I'm going to allow myself to do this. So using linearity here, using the linearity of the inner product, we are going to say that this is equal to well, I'll bring the half. I've got this coefficient here, a half of a naught, but that's the inner product of 1 with the function sine of mx. And then you've got a sum over every n greater than or equal to 1, an times the inner product of the cosine function with sine of mx. So just be careful you take it down right. The parameter here in the cosine function is n. The parameter here in the sine function is m for mother. Okay. So n is ranging over every positive integer value. M is just fixed at some particular value. And then I've got the second sum, the sum over all n greater than or equal to 1 of bn times the inner product of sine nx with sine mx. Okay, so be careful here. In the sine function in the first position has the parameter n multiplying x. The sine in the second one has the parameter m. This n is changing. It's ranging over 1, 2, 3, 4, 5, 6, 7, all the way up to infinity. This m is always m. It's kept fixed at some particular value. So you can see what I've done there is exploited the linearity property of the inner product. Okay, we've said that the inner product of f with sine is the inner product of this big giant linear combination with sine, and then I've split that down as the corresponding linear combination of all the individual inner products. But what we're going to use here, remember that the inner product, or the family of functions, all the cosines, all the sines, is orthogonal with respect to this inner product. So here I've got a load of individual inner products, but they're all inner products between functions in this family. But this family of functions is orthogonal. So most of those inner products on the page there are all equal to 0. We just proved, one of the previous examples in this class, we proved the inner product of any cosine function with the sine function was always 0. So this whole infinite sum here, sum of ANs, is all 0. Secondly, the inner product of any constant function 1 with one of the sines, that has to be 0. Most of these inner products here are 0. Because most of these, in fact, all but one of them, it's the case that it's an inner product of one signed function with a different one. One of these inner products will not be 0. And that's when this index n, it starts at the value 1, it's going 1, 2, 3, 4, 5, all the way up to infinity. At some point, it's going to hit this value m. And then you'll have the inner product of the sine of mx with itself. And that value, we worked out in the previous example, is equal to pi. So that's the only time one of these inner products on this line is non-zero. All of them are 0, except for this one here, when n takes on the value n. Okay. So everything disappears from this huge sum except bm times the inner product of sine of mx with sine of mx, which is bm times pi. Okay. And that's due to the orthogonality of this family of functions with respect to this inner product. So therefore, you take this equation now, you see you've got bm times pi. This is the inner product of f with sine of mx. That's the equation, that's the conclusion we're picking out. This gives us the required formula for bm. Okay. So it's not a proof of that formula necessarily, but it's kind of a proof that if we assume there is any kind of Fourier series, then bm has to be given by this formula. Okay? And this is something that can be evaluated. If you're given some particular function f, then we can use this, we can evaluate the inner product here and obtain the value of the Fourier coefficient bm. Similar arguments to that one we've just done will motivate the other formulae as well. The ones for a0 and an. Okay, I had hoped to go and do the example 3.4. That would be the next thing to do. See, because in example, in the introductory lecture last time, we looked at the Fourier series, we looked at the graphs, the various Fourier series for the square wave function. So example 3.4 is actually going in and doing that. So, but we don't have enough minutes to go through it. So to prep for the tutorials, I know some of you have a tutorial this morning or you just had one. But to prep for your next upcoming tutorial, attempt example 3.4. I mean, it's more or less worked out. It's more or less worked out there. We'll work through that. And exercises 3.1. And you can be discussing exercises 3.1 in your next tutorial, either Friday or next Monday. Okay, so thanks for leaving it there for this morning.